In this video, I'm doing another optimization problem. This is another resource optimization type problem. So take a moment and read over the example. Okay, from the example, the first thing that we need to determine is what is the objective function? What is it that we are trying to actually maximize or minimize? And in the very last line, it says, what is the largest area? So we're trying to maximize area. And we know that the enclosure is rectangular. So from that, we know that the area that we want to maximize can be represented by length times width. And so I'm just going to draw a little picture here of a little rectangular area. And so this would be the length, and this would be the width. And we want to maximize that. So this is our objective function. But the objective function has two independent variables, length and width. So that means we need a constraint. So we need to look a little bit further into the problem to figure out how can we relate the length and the width in another equation to create the constraint. And for that, we're going to go to this line where it says the fencing for the east and west sides costs $3 per foot, and the fencing for the north and south sides costs $9 per foot, and the company has a budget of $295. So our constraint is a budget constraint. We have a budgetary constraint. And so the left and the right sides would be the east and the west sides. And so let's come up with an equation for that. We know that this side here costs $3 per foot, and W represents the number of feet. And so this side over here would cost $3 per foot, and W, width, represents the number of feet there. The north and south sides cost $9 per foot, so that would be 9 times L and 9 times L. So whatever the length is here, we would multiply that by 9. Whatever the length is here, we multiply that by 9. And likewise with the widths multiplied by 3. So that means 9L plus 9L plus 3 times the width plus $3 times the width has to be equal to 295. Now, technically, we could make an inequality out of this. It says it would have to be less than or equal to 295. But for the context of this particular problem, we're just going to go with saying that we want it to be equal to 295. Well, this is our constraint. Okay? This is the constraint, a budgetary constraint. But of course, we are going to want to simplify that. So 9L plus 9L would be 18L, and 3W plus 3W would be 6W, and that's equal to 295. And then we want to solve this for L or W. So it really is quite arbitrary. I'm just going to solve it for L. So 18L is equal to 295 minus 6W. So L is equal to 295 minus 6W divided by 18. And now we can substitute that into our objective function. So the objective function is area is equal to length times width. Well, the length now is 295 minus 6W over 18 times W. So we've gotten rid of L. Well, we can simplify this just a little bit. And that means that we would rewrite this as 295 divided by 18. I'm just going to leave that as it is because it's going to come out as a decimal and I don't want to round, times W, minus 6 over 18. Well, that's 1/3 W squared. So multiplying by the W, dividing the 6 by the 18, and the 295 by the 18. So this is now my objective function ready to be optimized. So the three-step process, step number 1, determine the objective function. We've done that. Step number 2, determine the constraint. We've done that. Step number 3, substitute the constraint into the objective function. We've done that. It's now time for step 4, which is to optimize, which means we want to find the derivative of A with respect to W, because that's our independent variable now. So the first term, we're just going to have 295 over 18, and then we're going to have minus 2/3 W. And we want to set that equal to 0. And solve that for W. So we will have 2/3 W is equal to 295 over 18, or W is equal to 295 over 18 times the reciprocal of 2/3, which would be 3/2. Well, 3 cancels with the 18. 3 goes into 18 6 times. So this reduces to 295 over 6. And I do believe that's going to come to approximately 24.6. So that's rounded to the tenths place. So W is 24.6. That would be the width that would answer our question. Well, now we need to find the length that would answer this question. So for that, we go back to our constraint, which relates the length and the width. The length is 295 minus 6W over 18. The length is 295 minus 3W over 18. Substitute in W, 295 minus 3 times 24.6, all divided by 18. And this should end up being approximately 8.2 when you round it to one decimal place, 8.2. So we now have the width and the length. I believe it also asks for what is the maximum area. Well, now that we have the width and the length, the area is simply length times width. So if we multiply these two together, 8.2 times 24.6, we end up with approximately 201.72, or just 0.7. And so the width is 24.6, the length is 8.2, the area would be 201.72. And one last thing that we want to do just to make sure that we are maximizing is we want to find our second derivative. And so the first derivative is 295. I'm going to do that right up here where I've got the first derivative to look at. Here's my first derivative. So real quick, the second derivative test, the second D test, we take the second derivative. Well, the derivative of constant is 0, so this just becomes negative 2/3. So the second derivative is always negative. In other words, it's always going to be concave down, always, which means we have no choice but to have a maximum. So we have found the dimensions that will give us the maximum area.